Okay, thank you very much. I want to talk about nonlinear characterization and simulation of zinc-oxide search arresters. First, I will begin with an introduction and explain what search arresters are and why we want to simulate them. Then I will describe some measurements which are done to estimate the electric conductivity of search arresters. These parameters are used for electro-thermally coupled simulations, which I will show some results. I will show the end and conclude. We want to develop methods for the numerical simulation of search arresters, and for this purpose, we also need to improve our knowledge about Varistor materials. There are various aspects in which we can improve search arresters, but in principle, at the moment, we are working in two aspects. We want to simulate what is going on during a lightning impulse, and we want to simulate to know if a search arrestor is still thermally stable after one lightning stroke or a series of subsequent lightning strokes. This is of increasing importance with simulations for search arresters which are working for at ultra high voltage levels. Search arresters are used to protect electric networks. At the right-hand side, you can see a scheme. In the middle, there is a stack of metal oxide varistors, which are central element of search arresters. And here in this porcelain house search arrestor, you have on the outside porcelain housing with shielding structure, and between the central stack and the outside porcelain housing, you have a gap of filtered gas or air. For this presentation, I did a studio simulation. This is a model of a search arrestor as it is described in ISC standard. It's no actual search arrestor. I want to simulate the voltage spread. If I know the electric fields inside the search arrestor, I can calculate the heat losses. And if I know the heat losses, I can calculate the heat distribution when I know the dissipation of heat. For this purpose, here in this case, I assume that a certain value of electrical conductivity and of permittivity. As you can see on the picture, the heat losses are almost the same inside the search arrestor stacks. That is not the case. Actually, it's not the case, but it's due to the fact that here in this simulation, I just use constant electrical conductivity. In fact, if I want to really simulate it, I have to consider the nonlinearity of this electrical conductivity. And even if the excitation is linear, harmonic, due to the nonlinearity of the material, I have to use a transient solver. And here you can see a result when your transient solver is used. In this case, permittivity values are used. One can see that the electric field strength is highest for the uppermost arrestor unit. And yeah, I already said that the metal oxide varistors have a nonlinear electric conductivity. The conductivity depends on the electric field strength. They are called varistor because they have their characteristic property is that they have a variable resistivity. At the bottom, there is a plot which was derived by Bartkowiak almost 15 years ago. It is showing the behavior of the electrical conductivity as a function of electric field strength over a wide range. We have three ranges. One range at very low electric field strength, where the conductivity is almost constant. One range at high electric field strength, the conductivity is also constant but much higher. And we have a range in which the conductivity is changing by, here in this case, 30 degrees of order. For actual varistors, which are used today, this range is smaller. We have maybe 9 degrees of order, but that's still an enormous factor of. And we have also the transition range is higher electric field strength. We observe different difficulties for numerical simulation. First, we don't know the real properties of this material. Here is shown the one curve as we would like to have it, as was derived by Bartkowiak some years ago. And normally, you don't have any temperature dependence. Temperature dependence is quite important, as you can see. And during many of our simulations, we cannot only have to include the temperature elements too. We cannot only not only interested in a function, in a relationship between our conductivity and electrical field strength, but we need to know our functional relationship between conductivity, field strength, and temperature. Because during a lightning stroke, these varistors can heat up by 100 degrees Celsius in a matter of microseconds. Second point is that we have a degree of nonlinearity, which is very large. If our solution, our potential is changing slightly, we can have a new solution which has more different electric field strength, and conductivity may be completely different. That means that our solution is converging very slowly or not at all. And the second problem is that we have to calculate the electro-thermally coupled problem. That's probably the smallest problem. We are doing measurements. We have done measurements with several varistors to determine conductivity. Each varistor has a different different properties. The manufacturer is printing a value on this varistor, which is rated voltage. And we had a lot of varistors of the same type, and we were picking 6 of them, which had almost the same value. They were heated in open to 300 degrees Celsius and let to cool down. At different temperatures, we subjected them to a current impulse, as shown here at the right-hand side. We have a varistor, which is between the lower electrode, which is connected to ground, and the upper electrode, which is used to inject the current. The current signal is shown here. It's a long-duration current impulse with a virtual duration of 2 milliseconds. During this current, our varistor is heating up by 140 Kelvin, and we call it both voltage and current. By recording these values, we could calculate for each sampling point our electric conductivity as a ratio of our current density and electric field strength. And what we want to gain the relationship between conductivity, temperature, and electric field strength. Temperature is still missing. We cannot measure temperature, but we calculate the temperature. We use the initial temperature at each measurement, and we know determine the heat losses, because we know our current density and our electric field strength. We also need to know our volumetric heat capacity, which is also nonlinear. So we get our conductivity, we get our temperature, and we get our electric field strength. And by multivariate regression, we obtained a relationship between these values, as shown on the right-hand side. We can use these parameters to simulate the electro-thermal coupled problem. Here on the upper hand side of the equation is the electrostatics equation with a scalar potential of phi. And the second equation is the heat conduction equation. The second term is lambda is describing heat conduction, and the term on the right hand side is describing heat sources. Both equations are coupled first by present temperature is influencing our electric problem due to conductivity, and our heat flow is influenced by our Joule losses. This is our computation scheme of our program. We are calculating in 2 dimensions only, considering the problem is axially symmetric. First, we are calculating an initial solution. Then we are starting with a loop. We calculate an electrostatic solution. Because the solution is nonlinear, we require several iterations until the solution is converged. With this vector of electric potential, we are calculating the temperature distribution, new temperature. If temperature heat flow equation is also nonlinear, so we need maybe also several iterations. And then we test if the temperature has changed so much that we have to start again with our electrostatics equation. If that is not the case, we advance in time. How could we test if our parameters are right? The easiest way, or the only way we could do it simply, was to use the same measurement setup for our simulation. We had to pick a cylinder of Zinc-Oxide with parameters which we had just determined. At the bottom was set to zero potential, and to the top surface we injected the total current, transient total current that was measured. And here we can see the measured and the simulated voltage signals, which are sufficiently close to each other so that we said, okay, we can use these values. But that's not the case. We want to use values to simulate larger problems, complete search arresters, or at least an arrestor unit. In this case, there's no sense in using a 2 millisecond signal for such a structure, so we need either shorter impulses for use for lightning, or we need a harmonic signal. In this case, we use the harmonic signal, 50 Hz AC voltage, but in this case, you cannot use such high electric field strength. If to say that during most of the time during a cycle, we are staying in a range where we have to use parameters which are not actually determined by our approach. And these are the results. We have calculated an effective voltage distribution, and from this effective voltage distribution, we are calculating an effective field strength. Field strength according to the effective voltage distribution. And along the central axis, the orange parts are corresponding to Varistor, and the blue parts are mostly aluminum, springs and other stuff. Yes, that's it. By this method, we had fewer measurements to obtain some more reliable data for electric conductivity, and we have also estimated the influence of temperature. Our limitation is that we have to neglect temperature capacitive effects, which are important by lower electric field strength. And okay, by this method, we have improved our knowledge about electric conductivity, and we can do simulations which you couldn't do before. However, for shorter impulses, we have to consider the non-specific effects. That means our electrical permittivity probably also nonlinear. And in any case, we have high computational costs. We have seen several loops in the circle in the scheme, and we have also very small time steps, so that our computations cost very much time, even if we have no resolution. Thank you.
Questions? No questions? Everybody tired? Okay, thank you very much. Thanks. Okay, next presentation is again given by CST, Mark Richlin from CST UK. He's talking about lightning strikes to carbon fiber panel and the electromagnetic and thermal effects.